given a whole family of networks, what will be the best. Okay, so now we're going to spend time with two networks from the 2014 competition that are really interesting, and you still see somewhat today, like not a ton, but still you see it, and they really start to become like, a lot deeper. These two networks, again, note, because this was just basically a change of convolution sizes and filters, same number of layers, nothing there, but in 2014 we started using some deeper networks, and these are BGGNet and GoogleNet. So the reason why we have two on here is one of these, BGG, won the classification. Let's see. It must be that GoogleNet won the classification task, but then, I think that's right. And then BGG won the localization task. So we've been talking the whole time. This is all about the classification task, but one took first, one took second. So I guess by the numbers here, this one took first, this one took second. They're quite different from each other, and lots we can learn from that. So we're going to go through both of them. And you probably, if if you've spent any time around convolutional networks, you've probably heard of BGG nets, and you've probably heard of GoogleNet, but it's now known better by another name, Inception net, and Inception version 2, version 3, version 4, and we'll go through some of those today. Okay, so BGGNet. So the first thing you should ask is, why is it called BGGNet? Because the two names on there are not. There's only two names. They're not B or G. But it turns out this is a group that was at Oxford, and they were in the visual geometric group or something like that, visual geometry group. So BGG is short for that. Okay, so breaking the tradition of being named after the authors, the first name of the author especially. Okay, so this is actually really interesting because these are much deeper networks, and they're way simpler just in terms of how they're constructed. So there are kind of two standard versions of this that you see a lot, and of course if you look at this, you can imagine having as many layers as you want. But there's a BGG 16 and a BGG 19, and I have AlexNet here as a for comparison. But the first thing you should notice here is that the size of the filters all the way through, from the start to the end, is the same. They're all 2 by 3. So kind of like the smallest meaningful sized filter that you could have, where you could you actually have some sort of spatial resolution there. And they're all stride 1. They're all pad 1. Pad 1 because it's 3 by 3, so it's preserving the spatial extent. And then every once in a while there's a pooling layer, and it's always 2 by 2, stride 2. And that's it. There's like nothing special. It's got basically the same head where it's going, 3 fully connected layers of size 4096, 4096, and 1000, and then softmax is the cross entropy loss. That's it. And the other thing to notice here is that these are kind of done in blocks, right? So from your input to your first set of convolutional layers, you have filters of size 64, and then those double to 128, and double again to 256, then double to 512. For some reason, we now have 3 convolutional layers instead of 2, and then we do that again. We don't go to 1024, we just go to 512. So there's a little bit of there's a lot of kind of simplifying what's going on here. We just use the same building blocks everywhere and just kind of repeat them over and over and over again, just building up the number of filters. Yep.
I was just wondering, so for when the network's trying to identify a task I, for example, might be for rotations, is that kind of like a pooling layer also? Like some images might have a task I kind of like.
No. What it really does is just like it just reduces. It's a really efficient way of reducing the spatial extent of your feature maps, and it really I think the way I think about it is that it's just more making it like less sensitive to exact placements of things, right? So if you're just taking like the maximum response in the 2x2 grid, then it doesn't really matter like where, like in your example, where that eye is or that piece of an eye is or whatever. It just matters that there's kind of something in that region to be detected. So it has nothing to do with rotations, just more like kind of basic jitter of the placement. But it's really just used as a very efficient way to downsample the image. Yeah.
So which layers has activation?
Oh, they all have. Yeah, they all have rate. Well, so all the convolutional layers have rate of activation.
But pulling doesn't have
No.
activation. How about fully connecting?
Let's see. Do they have radios? Yes, they have radios as well. Except for the activation. The activation after the last fully connected of size 1000, that goes to softmax. So that's not a radio. Softmax is the activation there, so that you're now ready. You now have a probability distribution, and yeah. So what that means is that you actually have a linear layer there. So yeah, each one has a linear. Each one is a linear layer, but it goes to softmax. So instead of going to radio. Yep. Yeah. And you can see like the only difference between VGG 16 and VGG 19 is
One more thing.
you just have more convolutional layers deep down in there, right? So, yeah. Okay, so why do this? Oh, I forgot to point this out. I mean, you saw it already, but you saw that there was like, this also represented a pretty significant drop in the top 5 error, right? Like this is not just like an incremental improvement, this is a big improvement. So like, what's going on here? Why does this work? So why use smaller filters, 3x3? Well, I don't know, there's like a lot of ways you could answer this. But one of the main reasons here is that smaller filters have just fewer parameters, just overall. You might say, fine, but maybe we need like 5x5s or 7x7s, to capture a larger spatial extent in the images or in the feature maps. And that's a good argument. If you think about AlexNet and you use 11x11 for the same images, it's there's these very large filters compared to 3x3s. That's true, but you can actually, when you stack these convolutional networks together, you can think of you can think of the way the 3x3s kind of go together in this following way. So the question is, what is the effective receptive field of 2 3x3 convolutional layers? And this is stride 1. And the answer is 5x5, right? So if I have a 3x3, so there's this 5x5 grid down here. And I have a 3x3. Each of the 3x3 subsets there is going to give me one unit in the next feature map. And that's 3x3, so one more filter will take me to one unit, one activation unit here. So you can kind of think of like 2 3x3s as being like a way of factorizing one 5x5, right? And you have fewer parameters, right? So you're getting the same receptive field for a single unit. You're getting the same receptive field size, 5x5, but you're doing it, but you're doing it with more filters, but they're smaller, so you have less parameters, right? Because if you have 2 3x3s, that's 9 parameters times the channel. But 9 parameters plus 9 parameters, that's 18, and then for the 5x5, that's 25, right? So it's small. I think of it as kind of like having factorized the 5x5 filter. And not only that, you now have you've introduced these layers, so now you've allowed yourself to put more nonlinearities kind of in the network. So now you're able to learn like more nonlinearities as a result. So so fewer parameters, more nonlinearities. You're getting deeper. So you're able to sort of learn better representations of the data set that you're training on. So, yeah. So this is something that's really been, like, since this has really been kind of kept with for newer architectures. It's just kind of stick with 3x3. Although every once in a while you still see the first, like the initial convolutional layer might be larger than 3x3, but then everything after that is just 3x3, if it's not 1x1. Okay, questions about that? It's just fewer parameters, but kind of able to cover the same amount of or the same size receptive fields.
Do you know if they're using padding on these?
Yeah, there's padding.
So
It said in one of the earlier slides, pad 1. So 3x3 pad 1, so you're preserving the spatial extent. And I have a slide here in a second that will go through like all the parameters. Yeah, here it is.
Would there be a reason why I'd break down at 2x2? Like instead of having 2 layers at 3x3, then you go to 4 layers at 2x2?
Oh, 2x2s. Yeah, so you typically don't do these even size filters for the convolutions because you don't have a center in that filter. I mean, you can do them. There's nothing stopping you from doing them, but you typically only see these odd number 3x3, 5x5, 7x7, and so forth because you want a center in the filter, and that it sort of makes the math of like striding and things like that kind of work out better. But I mean, you could do it, but you never see it. You just never see it. And if you think about it too, what would a 2x2 learn? You know, like what kind of spatial, like it's really, it's like side by side pixels, right? So, 3x3 at least has just a little more spatial extent there to kind of learn a little more interesting feature than just like side by side pixel features. So like, like your edge would be literally, like change from this pixel to this pixel instead of it maybe being allowed to be over like one more pixel, which when I say that doesn't sound very important, but I don't know. You just never see it. But heck, you can totally do it if you wanted to. Nothing's gonna, TensorFlow won't stop you, PyTorch won't stop you. No errors will be thrown. Okay, so here's a lot of numbers. So this is so for ImageNet with the input of 224 by 224 by 3, what you're seeing here is kind of keeping track of memory required for so you have the number of parameters and the memory required to for the feature maps as you pass them through. So the point to see here is one, like there's a ton, like just touch on the blue for a second here. There's a ton of parameters, right? So already, I mean, like just look at this. This one layer right here has 102 million parameters. This is just that one fully connected layer going from 25. Let's see, going from so 7 times 7 by 512, so 25K going to 4096. That like fully connected weight matrix is huge. So how many parameters does this thing have? So total memory requirement for the forward pass is 96 megs per image. So that's like a lot. Just for the forward pass, and then total number of parameters. So this thing has 138 million parameters in it. So, like, it's hefty. You need decent memory in your GPUs to be training up VGG. But funny enough, like the architecture was chosen in such a way so that you would have like you could go deeper, but like not have as many parameters. So like you can imagine how this would explode if they'd done 5x5 filters, all the way through, right? Like this would be much larger. So, interesting note. VGG is enormous.
This order or just many images, the memory is okay. So the hidden space needs to be saved for back propagation.
Right. Yep. Exactly. I mean, it kind of depends on the layer, but for convolutional layers, you need these. So yeah, you have to keep these things around. So notice that most of the memory is required early in the convolution and most of the parameters are late in the convolution. And that's happening because, you know, like we're working really hard to reduce the spatial extent as we apply, you know, our convolutions and our pooling, but we keep increasing the number of filters, right? Remember, like we said, I think it was last time, the number of filters, number of channels. You know, think of each of these as like encoding some kind of feature, like spatially extended feature. In this case, 7 by 7. So you have like 512 features, but each one of those is 7 by 7. Okay. So yeah, these are big.
Sorry.
Yeah.
Can I go to the last?
Mhm.
Okay. So you said this 96 megabytes is a lot because the training time, you need training time because it's problem.
Yeah, so this is on the forward pass, right? So this is, well, so this is for training, so the forward pass would be for training and test. But when you're training, you also need a back prop. So you have essentially like twice that requirement in the back propagation because you now have the gradient information coming backwards. So you've stored the forward information, the feature maps from the forward pass. Now you have the gradients coming back, which are essentially the same size. So now you have twice that, and that's per image.
But for the test time.
So test time, you don't have the back, you're not doing back propagation, so you'd only have the forward pass, right? So you'd only have the 96. And you wouldn't have to store them necessarily. You would just need as much memory as, you just need as much memory as, like the largest amount of memory needed per layer, per image.
No, what I'm asking is that for the test time, it wouldn't be a problem, right? Because it's just the weights are fixed and it's just calculating.
Well, you're storing all those. So we're not even talking about what was required to store the weights. So you have all that, and then what you have is you're taking these images and you're turning them into these like huge tensors, right? These feature maps, right? So this is like the memory requirement per image, you know, as it passes through the network. Like it's like all those feature maps, you know, added together.
So am I right to say if I have 10 pictures, then my memory should at least be about 960 megabytes?
If you
If
you have 10 images, then it's
in a minute edge.
times 2. Yeah, which like now you can buy a GPU that has 32 gigs of memory. It'll cost you $10,000, but you can buy these, and so these issues are like not as big a deal. But at this time when you had GPUs that only had like 2 gigs of memory, you had to fit the whole network in it. So all those parameters, 138 million parameters, and they're probably all floats at that time. So 32 bits per. So you have to store all of that, and then you have to have room to store all of this. And then this is just a big network. It's not such a big deal anymore, I agree, but it was way back when in 2014. It's amazing how it's like only 5 years ago. Not that long ago. It seems a long time ago. Okay, there's some nomenclature around this. The layers kind of have names. There's like the stage it's in, the convolutional stage it's in, and then like which layer within that stage. And this is pretty typical as you go to other architectures just to do this. You have a stage name and then within that stage. Like ResNet will see the same thing.
Nice. On the VGG16, because I just counted, it's 15 layers.
What's that? No.
I just counted it's 15.
No, there's
The software.
6, 9, 11, 15, and 16, 17. Yeah, why is it? Why is it 16? Is it not counting the pools?
I don't think so.
4, 6, that's 12, 15, yeah. So it's not
counting.
It's not counting the pools.
It counts the softmax, but doesn't count the pools.
Yeah. That's a good question. Okay, So, yeah, so like I was saying earlier, this took second in the classification task, but it took first in the localization task. So there's another one where it's, you know, like draw bounding boxes around the objects in the image. So this took first. We talked a little bit about how AlexNet was trained. It's trained in the same way. You can see this doesn't have those funny normalization layers. BGGNet was what gave the 19 was what actually gave the best result, but like for a single model. But for some reason, you have both of them still. You know, they're still both around. Like we saw before, if you use ensembles of these things, you actually get slightly better results. And this is actually where you see BGGNet come up over and over and over again. Is that people still use this embedding layer, FC7, so like that's. So if you take, so you train this thing on ImageNet, and now you take any image and you just, if it's of the right size, you can resize it to 224 by 3, and you can send it through here. So what you're getting a transformation of that image through all the layers, and then, at fully connected layer 7 there, FC7, you can just take that as a representation of the image. And that's used still like all the time for representing images and doing things with images. So like you can, I don't know, there's like so many different ways this is used, but you can do things like, are these two things like each other? So, or like do like queries. You could say, you can compute all these things. You can compute like the angles between them and the distances between them or something like that. And you could retrieve similar images, again, not of the classes that we saw in ImageNet, but just images generally. You could say like, what image is nearest this one by just asking similarity questions in that high dimensional space of size 4096. So anyway, this is where it's still used like all the time. And also it's this is used for like transfer learning still all the time, where you basically you take this trained network, you unfreeze. You think of it as all the weights are being fixed, but you sort of like unfreeze like the last couple of fully connected layers, maybe just the last one, and then you train on your new task, and it's only learning like the weights for like the FC8, for instance, and then you typically have like a really high performing classifier, for instance, because like this network has really learned to just pull, to featureize images that look like the stuff that came from ImageNet. It's pretty cool. And then because this was like, this is so deep, they actually, to get this to work, they had to figure out an initialization scheme for the layers. So we're going to talk a little bit about that real quick. So yes, weight initialization. So what happens when all the weights are set to some constant? Just think about that for a second. We'll start going through this. So, okay, so I think we already mentioned this before, but like a really standard way that people were initializing networks was to draw random, parameters from a normal distribution, and then you could decide, how, like you can multiply by standard deviation, whatever one you want, and and then use that. The trouble is though, so that might work for smaller networks, but for deeper networks, it actually became a big problem. And I'm going to sort of just like lay this out a little bit for you. This is not like a proof, but this is definitely what the people at the VGG were dealing with here. So here's some code around just a very simple 10-layer network. There's 500 layers in each, or neurons in each layer. For ease of analysis, there's tanh nonlinearities, and then if they're initialized in the way that we just saw, then here's what happens at each stage of the network. So this is these are histograms of activations at each layer. So, you know, we drew these to be normal, so like they start out being normal, but it turns out that, you know, given that set of choices, really quickly, the activations just all go to zero. The activations just kind of push that Gaussian to have a smaller and smaller variation until basically all the activations are zero. And that becomes a problem because, like, basically there's not a lot going on in your network. There's not a lot to learn at that point. Yeah, like what happens in a network like this where all the activations are zero? So you get to your loss function, all the activations are zero. So you get to your loss function, what's up? Well, your loss function is going, you know, so it gets to the cross entropy. So it gets to the softmax. What's the softmax going to look like? It's going to be a uniform distribution, right? Because whether these are all zeros or whatever, if they're all the same number, you're going to get all the same scores, and you're going to have a uniform distribution there. So you are going to have some signal from the loss function because you're going to have a uniform, and it's going to say, wait, one of these is right. The thing is, though, it's like there's no signal there to like grab onto that, like differentiating, other than just that one. It's like you start to see you start to see various examples here. Like it just gets confused and doesn't learn anything. Basically, no learning happens here. So, anyways, it's a really bad way to initialize. There were some other ideas for initializing, like let's not make the let's not use like the normal distribution here, let's just use I guess we're saying the center one here, and you get sort of an opposite behavior where you get saturation out to the side. So like you get, instead of everything kind of all the activations going to zero, now you get all the activations pushing out to 1 and minus 1. You remember this is a tanh. So like neither of these are good. Neither of these ways of initializing are great here. So the question was like, what do we do here? And so they figured out the following, which became known as Xavier initialization, which I believe that's the first name of this guy, Leroux. But anyways, so what they figured out to do, and in this paper, they actually, using activations that we would never use, linear activations, they came up with this formula for doing initialization. So again, you're drawing from the normal distribution, but but the standard deviation is determined at each layer by how many neurons are coming, are part of the input, so how many neurons in the input of the layer. And so if you divide by the square root of that number, sorry, I didn't say this earlier. So fan in, fan out is basically, the number of neurons in the input, number of neurons in the output. So number of neurons in the input layer, number of neurons in the output layer. So if you do this initialization, then it turns out that mathematically, if you have linear activations, you can see that this actually preserves some nice properties of the distribution for doesn't matter how deep you go in the network. And then empirically, for that same example that we've been looking at, you continue to get nice distributions of normal distributions. So not pushed, not saturated out to minus 1 to 1, but not just all tightly centered around 0. So anyways, this became known as Xavier initialization, and is what allowed them to get some decent signal in training this network. Questions about that?
Why does this work?
It's something in between these two, right? So here you have a very small. Here, the normalization term is very small, 0.01, or sorry, I should say the standard deviation is small, 0.01. Here, it's very large, So you need something in between, like, you could toy around with that, that number and like find something, but it turns out that in the case of linear activations, you can prove that like you like preserve the standard deviation as you move through the layers, again with the linear activation, so no network that we'd actually ever use, but you preserve that if you use 1 over, so your standard deviation is 1 over the number of neurons coming in. So it's something like, so what that's saying, so number of neurons coming in, that's like, the number of like different signals you could possibly have, right? So that's like, it's like the number, like it was like the number of samples, right? So a square root of that is like it's like very close to like the unbiased estimate of the standard deviation for an empirical norm where you sum those up. So like from if you remember your Gaussian statistics, central limit theorem says you have the if you sum of independent draws, then that will converge to the normal, as long as you scale by 1 over the square root of the number of samples. And so that's what's happening here. So you're getting like the right kind of growth term here to preserve the normal behavior. And it's kind of funny because it's like it's proven in a situation that one would never be in, but you start with that and you empirically see that like this works, and so it's good enough. For like ReLUs or something like that, we'll see when we do ResNet, we'll see another kind of initialization that kind of redoes this, but thinking about the statistics that come out of ReLU activations, you get something slightly different from this. And we'll take a look at that in a little bit. Well, the next lecture on Thursday. Yeah. Go ahead.
So the initialization is just different from layer by layer.
Exactly. Exactly. Yep, it's different layer by layer. And obviously, like, all the inputs are not IID in each layer. I mean, you can't expect that at all. But still, it works empirically. So that's a bit of the justification for why. Okay. Right, so, I don't know, this is just more on their submission, their top 5. Let's see. I'm trying to remember. Yeah, so this is so their submission was an ensemble of these 7 different models. The D, C, and E, I've actually right now forgotten what those are. It has something to do with the way that they did data augmentation for each one of these, and I can't remember what it is right now, so sorry about that. Anyways, they had some of these things, they got great result, and then like with most of the best models, like they worked really hard to get something submitted by the deadline, and then they always did something. There's always something like a little bit afterwards that tends to be a bit better, but still took second place in the classification test, so. Woohoo for them. Wasn't good enough to take first though. Because what took first was GoogleNet, which became known as Inception. So it also ended up its best. So you can see that like this is really interesting. Its single network accuracy ended up being larger than this ensemble, but these two, are pretty dang close. But they got this submitted in time, and VGG group didn't. So it's still a loss, I guess. All right, so let's start talking about the Inception test. And it's literally called Inception because we need to go deeper. Yeah. It's exactly what I mean. This is not a joke. This is really true. So. So what happens in Inception? So VGG is just like, hey everybody, just do like the most basic convolutional stuff you can. I know it's a lot of parameters, I know it's a lot of memory, But if you kind of just get those numbers right and you initialize right, then turns out you get a really great classifier. So like that's really interesting because it just tells us like that we can think kind of maybe in a more principled way about the architectures of these networks and how to build them up. But then you have this network which actually wins the competition, and it's totally different. And it's so you can read this slide here. So it's got 22 layers, so it's deeper than the VGG 19, and it's modular in the sense that, like, it's built out of the same kind of pieces, but the pieces are these Inception modules. And if you look at it right now, you should be like thinking, like, what in the heck is going on there? Like this, it doesn't make any sense. And when I look at it right now, it doesn't make any sense to me either. But it's a cool idea. And we're gonna spend some time going through it. So the way this network works is you have your inputs, some standard convolutions, pooling, and so forth. But then you're built up out of you built 9 of these Inception modules, and then just one full connected layer to the softmax. You should also wonder, like, what is going on over here. There's a couple of other like heads on here that look like the top head, and they actually are. So this thing is actually supervised by 3 loss functions, all doing the same thing. So we'll talk about that in a second. But so yeah, this is really this is really different. And what's interesting about it is that it did better, and it's way small. So it's deeper, more layers, but it's way smaller than VGGNet, right? By like a lot, by like 20x or 21x, or else 132, so way more than that. I mean, this is way smaller. All right, so how does this work? How does this do this? Well, I don't know. These guys were at Google, like, just trying all kinds of crazy things, and here's what they came up with. So, yeah, the Inception module. Let's take some time looking at this Inception module. So the way this thing started off, if you read these papers, these are a great set of papers that start with this model and then kind of work through version 2, which introduces batch norm, and version 3, which does more factorization of the filters, and then version 4, which combines it with residual networks. And there's just a lot, like, these papers are really well done because they spend a lot of time kind of motivating how they thought about this problem, which is great because, like, when you're looking at this, you're probably going, like, how do they possibly come up with this? So the way that they thought about this was they were like, okay, like, we don't know if we ought to be doing convolutions of size 1 by 1 or 3 by 3 or 5 by 5, or we should do max pooling. Like, let's not worry about that. Let's not worry about choosing. Let's actually do them all. At every step, in every module, let's just do them all. Let's actually take the input and do 1 by 1 convolution, and 3 by 3, and 5 by 5, and max pooling. In this case, they chose 3 by 3. And then let's concatenate all the filters that come out of each one of these together, and now that's the output to the next layer. And like, that's not a bad idea, right? Like, why not? Who says you have to kind of just, you can only do, from the input, only do one type of convolution layer. So they were definitely thinking outside the box, and yeah. The trouble with this, though, is that there are a lot of parameters here. So let's go through this a little bit. So let's go through this example. So the input, we'll say we're at some point in that part of the network where the input is 28 by 28 by 256, okay? So activate that. And then for some reason we choose these numbers of filters for each of these types of convolutions. So it's going to be 128 1 by 1s, 192 3 by 3s, 96 5 by 5s, and then your 3 by 3 pooler will just have 256 again.
Module input, remember if an image should have 3, right? Module input.
So this is just somewhere in the network, right? So this is the feature maps are just the 28 by 28 by 256.
Oh, it's on the
Yeah.
middle there.
Yeah. This could just be C. Doesn't matter how, doesn't really matter how many there are here, just some number of channels. Okay, so, question 1 here. What is the output size of the 1x1 with 128 filters?
28 by 120.
Yep, 28 by 20 by 128. You don't have to worry about padding or anything like that. This is just 1x1s are just 1x1s are just doing the convolution in depth direction. Okay, so yay, we got that one right. How about the next one? I can't remember. Give it away already. How about the rest of them? So the question is whether or not we do padding or not, right? So we're going to concatenate everything here at the end. So what should the spatial extent, if this is the spatial extent of this of the 1x1 convolutional layers, what does the spatial extent of these need to be able to concatenate all the filters together? It needs to be the same, right? So what will we pad by here for 3x3 convolutions? Pad size.
Supposed to be happy with like 0 by
Pad with size what?
1.
1. Well done. And with 5x5 pad with size 2. All right. So yes, we're going to get so out of the 3x3, we're going to get 28 by 28 by 192. The 5x5 is 28 by 28 by 96. And then the pooling doesn't change the number of filters, so we stay still have 256. So what's the size of the final output after concatenation? Well, it's whatever 128 plus 192 plus 96 plus 256 is, which ends up being 672. So in this one module, you went from 256 to 672. That's a pretty significant change, and there's a lot of parameters here, right? I mean, obviously we're like doing all kinds of convolutions in this module, so there's a ton of parameters here, and yeah, so there are all the ops required. So anyways, very, very, very expensive. So what can we do about this?
Sorry.
Yeah.
I think how the max pooling layer here works should not be reduces the width somehow. It's a max pooling.
Well, so yeah. So you're saying like on the 28 by 28 here?
Yeah.
How does it preserve that? So the way that this works is that you use a stride 1. So right, you would also pad with the 3x3 with size 1, but here you instead of striding by 2, which is what gave us the downsampling, here you just stride by 1. So you do preserve the size. Okay, so this is a good idea, but it's going to be way too slow. So what do we do instead? Well, the idea that they came up with was like, hey, let's just do a whole bunch of 1x1s going into this and reduce the size of the input. So yeah, we can talk about 1x1s. They're great because they're essentially the way, a very simple way, like a nice learned way of preserving the spatial extent but changing the number of channels. So the way this works is that they just put more layers in. But they made a 1x1 so that they could reduce the size, the number of channels going into it. So this idea of think of it, so they call it bottleneck layer. So you're pushing something in that has like, C number of channels, but then you use the 1x1 to really compress it. And then you do these convolutions, and then you could expand it back out again if you need to. And so that's what they did. Maybe seems kind of silly, but maybe like it adds more computation, but it doesn't add more computation because what's happening is, again, so you have your channel depth convolution here, which is in addition to what we had before, but now that you have so many fewer channels, the output here is going to be much smaller. And this is just kind of general idea of bottlenecking. So, like, here's that same example again, but now going from 256 to 64. This 4 times reduction is like really common, and yeah, and so now you have fewer ops in general. Like this is like half as many, or like less than half as many. So they use this strategy for kind of making each of the modules a bit like less computation intensive.
I just don't understand this one. So why does for these two, the 1 by 1 is beforehand, while for the pulling, 1 by 1 is afterhand?
Because you're just yeah. So what you're allowing for here is just pool first and then learn the convolution. You could do it before, you could do it after. And they in the paper they explain that there was some advantage to pooling the original feature map and then compressing it rather than the other way. But you're right, you could have done it.
Oh, you mean pulling it because it shrinks the size, or?
But it doesn't, because we're only doing stride 1 here, right? It's just like it's a transformation. It's just so like a 3 by 3 with stride 1 is like a so I would think of it. It's not downsampling because you're preserving the spatial features, but you're making like the spatial features very redundant, like way more correlated with each other nearby, because the match is likely to be the same in nearby 3 by 3 pools.
So you're kind of making like a block, right? But
Yeah.
It's a picture, you're making a block.
Yeah, you're kind of like, I'm trying to think of what the right word is for that. That's a good way to say it. That's exactly in my head. Exactly.
Like for the pulling layer, it also had
Yeah.
the side, yes.
Yeah, that's right. But you probably wouldn't pad with 0, you'd probably pad with like negative infinity, so that you never, because it's max pooling, so you would never use the padding values. I mean, it's just conceptually. Okay, this is what they did. You can ask many more questions about what they thought, and I couldn't tell you. This is just what they did, and it won. So if you win, you're the victor, you write the history, you're always right. So not only did they do this, they just stacked these things up. Like I said, we kind of night them, right? So, cool. These actually are pretty slow to train, even though they have far fewer parameters. There's like a lot of computation going on in each of these modules, so they're pretty slow to train, but they work. And so we're gonna think about the pieces of this here. Now it's turned on the side, a little easier to look at. So you have this initial part of the network. This is just convolutions and poolings and convolutions and poolings. So this is conv, pool, and I can't see what's written here, but these are like this is a kind of norm. I can't remember what norm is used there. I don't know. I'm forgetting what's the red. I'll open the paper because I can't read what's there in the picture. But they're basically there's convolution pools with some activation, and then you start building up all the Inception modules, and then you just have a very simple output. And there are, if you read before, there are no fully connected layers, it says in this, which is true, although if you're looking here, you're like, wait, that's a fully connected layer. But the point is like this did like a max pool, or like this is like a global average pool, and then this is just like the fully connected is just the linear to the soft max. So it's fully connected, but it's just the one transformation that you need to get your output into the right size for the classification problem. So it's not, doesn't count in the author's mind as a fully connected layer, because it's not like a transformation with a followed by it. Do you have a question?
Well, I'm just curious, maybe you'll address it in a minute, but you have these three heads.
Yeah, but we'll talk about it right now.
Okay.
Yep. So yeah, so remember how the fully connected layers were the ones that had, like, especially at the end of the network, had like, they were contributing a ton of parameters to the model, right? So what they do, right? So what they have right here is an average pooling layer, which is basically for each for each of the filter maps, you know, each channel in this last set of feature maps, they just average they average each map, each slice to one value, and that just gives you like now a vector of size, however many channels there are at the end, and then that's transformed via linear transformation, so matrix multiplication. So like a fully connected layer, but you know, for ImageNet, you know, to size 1,000, and then you apply softmax. So instead of like taking all the parameters in the final like spatially extended feature maps and then stretching that out into some huge vector and then doing a linear transformation to some other size, they again they collapse the spatial extent by doing an average for each channel. So, and this is actually used a bunch now for all kinds of networks. It's just it just you don't get that huge blow up in the number of parameters from those last couple of full layers.
I feel strange that when there are additional two.
Yeah. So like you're not the third person to ask that, and I will address that right now. Okay. So what they found was that this network was getting so deep that they were having a hard time propagating the like gradient signal all the way back to the beginning of the network. So the way that they solved this was to basically take the exact same network here or head here, although you can see there are two fully connected layers here instead of just one. But basically taking that and attaching it like closer and closer to the beginning of the network, and it's basically just so it's being supervised by the exact same problem, right? So it's exactly the same softmax. It's just the gradient from this softmax is like fresh right here in this part of the network and is propagated backwards.
It's like a bite-sized version of itself.
Yeah, I mean it's just you know, hey, this is called Inception, so why not like have more like repeated elements, right? So it's just really they just discovered that they could do this, and like this really helped to supervise the whole network. So in very deep networks now, like residual networks, you don't have to do this. The way that the residual networks are designed, you don't need to do this. But before you had like residual units, you did something like this, and it worked.
So now you have three loss functions. So are they trying to minimize the
Oh,
average or sum of all
the sum of them.
Any weights or equally weights?
Yes, there are weights. I forget the details now, but like the last has the highest, and like this has the lowest. But yeah, again, those are just hyperparameters in between.
So does the gradient from the loss function at the end still go through the whole network?
Yep.
Does it just?
Yeah, I mean, like it's still back propagated, right?
Okay.
And then this gradient, like the gradient from here, you get the sum of the gradients here at this layer, and then the sum of all the gradients here, and then then it's just back propagated, and then it just all comes together, and you don't know about it anymore. But yeah, it's just an interesting way of kind of strengthening that gradient signal. Yep. Okay. Yeah, so here's the justification for how they count out the number of layers. They counted 2 layers per Inception module, right? Because you have like the 1x1 convolutions, and like all the 1x1s and the max, that's like 1 layer. And then all the, like this 1 by 1, and then the 1 by 1, 3 by 3, and 5 by 5, those just all counts in the layer. So I suppose they could have said that this was way deeper than that because they have all kinds of layers everywhere, but they were conservative. So anyway, that's how you get 22 layers. Not that it matters much anymore because people train with like 150 something layers. So 22 is quaint. Okay, so questions about Inception? Very strange, right? Like very, very different. It's it really interesting to think about. Like VGG is a super straightforward convolution pool, convolution pool. You know, all the same size, whatever. Just change, double the number of filters. Super straightforward. This is like, let's throw the kitchen sink out, all the convolutions we can think of, pooling. Let's supervise this 3 different times, but it has way less parameters, and that means the competition. So there you go. Yeah.
So when they do real test time prediction, it doesn't take into account the 2 auxiliary
Oh, I see what you're saying.
endpoints.
Yeah, that's a good question. Let's see. Yeah, I think what they did was they averaged the predictions from all of them, like using the weights that they used in for when they rated the losses.
Okay.
Although I'm not totally clear on that now. Kind of forgotten that detail. But yeah, you're right. You can make predictions from all of those heads. Yep. Okay, so Inception, like a little cottage industry kind of grew up around Inception type models, and especially the same group of people. This is Christian's Shizgegi et al. And they started doing a lot of really innovative stuff along these lines. And like one really important thing that they did next, which you can think of as Inception version 2, is they introduced this idea of batch normalization. So you've probably heard of batch normalization before, but the idea is, like you see here, the idea is for each batch, to basically rescale your outputs so that like that batch has up to this point at least has 0 mean and mean variance, so that the stuff that you're passing on to the next layer of the network has a fixed distribution, has an expected distribution, and this actually really revolutionized like a lot of what was going on in convolutional networks, and it's now used, or like variants of it, like everywhere. Everything's got this in it. So I wonder if you brought it up at some point, like in the past. But again, like the idea is, if you think about it, like you pass in any batch, at any layer, like the distribution of activation you can get there could be like literally anything. Like, yeah, it could be anything. And so if you think about it, what that means is that the next layer has to become robust to like all these different types of distributions and activations. And the thought was, wouldn't it just be simpler if like all the next layer had to deal with was just knowing that these things were going to come from like a zero-centered unit variance distribution. We're not saying it's normal, so definitely not. Doesn't have to be normal, but it just just if you kind of fix the mean, you can fix the variance. And like these are 2 parameters of the distribution that the next layer doesn't have to think about. Because it's always going to be the same every time. It doesn't have to learn like how to deal with those. It doesn't have to learn how to like normalize those. And so so just make it so. From your batch, estimate the mean, estimate the standard deviation, or the variance, and divide, and take the standard deviation, or take the square root, divide by that, and now you've got it. This actually was really, really, really powerful. What they did was they introduced these between. I forgot about this. Yeah, like the original Inception actually used can't. I forgot about that. Naughty, naughty. So anyway, they put these between whatever your activation was. They put these between, you know, your output from the previous layer and the activation. Actually, there's now evidence that you should put it after the activation, and we'll talk about that when we talk about resonant. But this is what they decided to do. So it says fully connected there, but you could have the composition or whatever. And yeah, so so they did that. Like that seemed to work really well. But then they did this additional thing that was, I think, really really smart, and that was okay. So we'll do that, but let's just allow the network to learn two more parameters, or at least two more vectors of parameters, that allow us to scale our standardized output. So scale it by some factor gamma, and then shift it by some factor beta. So, maybe it's not. Maybe we're imposing too much if we make everything, unit variance, or zero-centered unit variance. Maybe let's just let the network decide what it likes to have come out of these things, and that's what they did. So this would change. This changes the centering. So instead of being 0, it would be beta, and this changes the scale to being 1 with beta. So they did this. They introduced these parameters. They're now learnable. You backprop through these, it's just a bit of a generalization from what we're doing before. In fact, it might even be better than before, because if the original distribution was okay, this can learn the expectation and the standard deviation, so that this could become an identity map, or this could become the identity map. So, anyways, they made that change, and this was really, really powerful. So this is known as batch normalization. It does a ton of things. So, like gradients. So once you start doing this, you get gradient flow through these deeper networks, because these distributions are just there's more signal being passed through at each layer. You can be a little more sloppy in your choice of learning rates, because it turns out the network becomes a little less sensitive to to the precise tuning of the learning rates. This doesn't require such precise initialization anymore, because it sort of can fix bad initializations really rapidly. And it is a kind of form of regularization, and there's still thoughts on this. Ian Goodfellow has an interesting talk from a couple of years ago at one of the conferences, where he now thinks of it as a way of making each layer independent from each other. But anyways, it's super, super useful. It's now in all kinds of convolutional networks. One thing you should be wondering about is this whole algorithm is defined in terms of what's happening at training, right? So we pass the maps through, and we calculate the statistics, and then we transform and so forth. But what do you do at test time? At test time, you're in a very different regime, and you don't want to. It would be like cheating to use the statistics from the test distribution to do these kinds of things. So the way this works is the actual algorithm keeps a running moving average of all the parameters here, so your means or standard deviations. Not the gamma, you just learn parameters, but of your means and standard deviations, and uses those at test time. So you use a moving average to kind of build up. It's kind of an online estimate of the actual average of all the data passing through there, the statistics for that data, and then you just use those at test time. So you don't calculate the statistics of the test batch. You just use the moving average from training time.
Explicitness, you mean like to a single fixed empirical mean and also standard deviation, right? You mean?
Yep, that's right.
And also we use the final step, also final iteration, yes, divided from the final iteration.
Yes, but it's a moving average, right? So it's like, think of it as like an online estimate of all the data that's run through it up to that point. So yes, you use it at the final iteration, but it's not the mean from the last batch. Like you don't. So yeah. So there's like two of these being kept track of. The one is like the per batch mean, and then there's another one which is the moving average, which takes this as like the update from this batch to the moving average of all of the mean that you're going to use or the standard deviation that you're going to use at test time. Yeah.
If you use the statistics from the test data, will it work better?
That's a good question. I actually don't know the answer to that. That'd be a great project to explore. I don't know the answer to that. It's like it's cheating because it doesn't. You're using some of the test data to give you to like estimate your generalization error. So like that's why you don't do it.
Why is that?
Because you're using statistics from the test data to help you. Like anytime you use anything in the test data to make your prediction, like any property of the test data other than like the sample itself, then you're no longer getting as good of a estimate of your generalization error as you could possibly get.
So the I here, it denotes the sample index, not the neuron index. Yeah.
Right. So, yeah. Yeah, and also, like that's going to change depending on how large the batch is. Like, you have a fixed size batch for your training, but you could conceivably like do this for like individual samples from the test, like one at a time, or you can do it for the whole thing. Like, you don't want it to be dependent on those kind of choices either.
And another question.
Yeah.
About the slides, one of the methods was called vanilla.
Yeah, so this didn't have, the plain vanilla doesn't have this final transfer. So this is like the plain vanilla batch norm. This, where you would then allow it to like recenter and rescale itself as learned parameters, that's like full batch normalization. Then that's really bad.
Is this done neuron by neuron?
No, batch by batch. So you can expand this idea. Like here's one way to do it, where you can like not only can you you can standardize it, but you could also like whiten it. If you get the covariances, compute the covariances, this isn't typically done, you can do these kinds of things. And then before we run out of battery here, I just want to, time's almost up. This is version 3, where they started to do even more like more factorizations of these original filters. So anyway, they started playing around with filter sizes and what goes into each module, and they did these one-sided factorizations of the filters, so you get even less parameters, but you still get you still builds up into the original, like you still get the same size receptive fields. It's really a cool idea, yeah, this version 3 got it all the way down to 3.58. So you remember like the original Inception was at 6.7 top 5 error. This is just using batch norm and using these different modules. You get now 3.58. So like almost a halving, essentially like a halving. It's like pretty awesome. Yeah, and a few other architectural changes. Okay, good. Questions? Yeah.
What you said about the batch normalization and the initialization, the value for sigmoid and time activation.
What's that? Sorry, I just understand.
The batch normalization and the initialization.
You can use batch normalization no matter what activation you use. It doesn't depend on the activation.
Actually, when we were talking about the activation, we were talking about the radio
I'm not understanding the question.
Actually, one of the advantages of the radio, I guess, was this that we don't need to normalize the input data.
No, you do need to normalize it. Like, you do need to use batch normals still. Like, yes, batch normals is used no matter what activation you use, because you're allowing the network to decide what's like the optimal distribution of the output going into the next layer. So this ability to learn that really improves not only your results, but your ability to get these results, your ability, to choose the right learning rate and to have deeper networks. Like these inceptions don't have to be supervised by additional heads anymore. These ones with batch normals, because the gradient's able to be propagated all the way through. Because the batch normal is it's kind of like rescaling, like at every layer, it's like being rescaled because of that distribution matching. Hope that answered your question, because I don't think I quite still understood it.
I don't know. The question was that if we change the activation function without batch normalization, if we get better result or not.
Oh, without batch normalization, I see. Yeah, like if you went from like a attached to a regular, you'd probably get better. You get better, but you would so that's probably right. But you would, now that we know about batch norm, we would always also use batch norm, because it just, at each layer just provides so much goodness. Yeah. Okay. We will finish up our history lesson on CNN next week.